Hello, everybody. Everybody, wow, look at all you bodies in here. I wasn't going to do a selfie because I wasn't going to see, I like to do selfies at my talks, but I didn't think I'd see you all. Well, I can't see anything, but go on then. I can't not do it. So we'll have to do it in two halves. So what I usually do when there's two halves, I'll stand over here, is that it's a competition. This side, you have to try and beat that side, and that side has to try and beat that side with the waves and the cheers and the looking really energetic at 10:20 on the first day of the conference. So yes, I'm expecting great results, okay? So, right, you lot are first, okay? I'll count you in. Good warm up, good warm up. Okay, so let me make sure I haven't got a thingy on my phone. You know a thingy? The pop socket thing? And so it's going to be, I'm going to try and not drop the phone. Okay, I have as many of you in as possible and my little face. Are you ready? 3, 2, 1, go! Go! And it was so dark it had to do it slow, like everyone stay still. It's going to be the blurriest picture ever. Right, you lot, you have to do a better job than that. I want more, okay? More, yes! Let me make sure you're in there. Are you ready? 3, 2, 1, go! I made sure that took them. That would be really embarrassing, wouldn't it? That was an excellent job. I don't know, I think they might have won. We'll see if, I'll give you another chance at the end. At the end, okay? I want really raucous cheering. All right, so it's lovely to see so many of you here for their forgotten AI of video games. Hurrah. I do have to give you a little bit. No, where has it gone? That, no. Where are we? This one. Oh, I was one too many. I was like, that's the one I wanted. This session does contain flashing lights and video game violence. Okay, if you're not okay with that, on your bikes. I'm not taking it out. All right, so let's go forward. I'm Layla. I used to be an enterprise developer advocate. Now I am a general dog's body, and I do anything that needs doing. I'm an accountant, script writer, 3D artist. I do everything at November North Games, which I co-founded with my husband. So I'm a Unity game developer. I've been doing that for over a year now, sort of, but with a caveat. But you probably know me more from Enterprise DevRel, like I said, and modular monoliths is what I'm really known for. I just did a 2-day workshop on that. But if we look at this was my first Unity Games book, Valentine's Day 2017. So I said I've been doing this for quite a long time, dabbling in game dev. So it seemed like a natural progression. I don't know why there's a blank slide in there. I must have put that in at 5:30 this morning. So we're going to talk about AI in video games. And AI can be used in lots of different ways in video games. We'll cover some of those. Well, we're only going to cover one aspect of that. We'll get to it. But you'll probably have seen there's like AI-generated animations now. You don't have to go into rigging and move the animations and tween between all the different animations. AI can do that, and it can get all the fabric flowing beautifully. So a lot of the big AAA games are using AI for their animation. You can do texture upscaling as well. So a lot of these remasters are upscaling their textures through the use of AI. We've also got things like DLSS, which is from NVIDIA, Deep Learning Super Sampling. So that means that you can run at a lower resolution, and it will upscale if you've got the hardware for it, so you get much greater resolution than your machine could maybe natively put out. We can have it for accessibility and code generation. We can have subtitles. We can have text-to-speech. We can have more stuff. I'll cover that in a moment. And it's also really good at moderating. I think there are several games. So League of Legends uses AI to reduce toxicity between players on their online game. So it has a lot of really good applications, and it can do sort of analytics and all that sort of thing. Okay, what is with these blank slides? Oh God, no, that's not blank slide. Okay, but AI in games traditionally was from NPCs. So this is Oblivion, the old one. This is all AI, okay. It totally threw me because I've got blank slides in front of me. Okay, good, all right. And then, this is the other type of AI. This is RimWorld. Let me get that play. There we go. Who's played RimWorld? Not as many as I thought. It's an excellent game if you want to lose all the time you have in your life. So here, it has AI-generated stories, and it's all about the stories. You are building the world, but everything going on is AI, and it has a very complex AI, and it's a really fantastic game of simulation and processes and all these things happening with your NPCs, your non-player characters. Okay, if I say alphabet soup and you don't understand it, yell at me and I will try and tell you what it is. There's going to be a bit of alphabet soup, but I will try and give you all of the results. So that's RimWorld. So this is another type of AI. And then, there we go. So here we can see, as I've said, we've got AI as part of the game. So that's part of the player experience. We've got as the content creator, so that is like the AI animations and things that, you know, are all in there, that the DLSS that I said, and then for playing, modeling player behavior, all right? So, and I tell you what is going on with my slides. They were fine this morning. Don't dabble with your slides before that. We're going to do AI as part of the player experience. That's where I mainly use AI. And the most recent thing in the news last week was this. In Fortnite, this is not the type of AI I do. This was like a ChatGPT style Darth Vader that streamer Loserfruit managed to provoke into swearing. So, you know, that's another use of AI for player entertainment. It's very cool what they've done, and it's pretty quick as well how it responds, and players can engage with that. But we're not doing that AI. That's far too complex for us. For me, really, that's not you, us, me. We're not going to actually touch any machine learning, neural networks, graphics AIs, or generative AI. That's not what we're talking about here today. I'm sure there are plenty of other talks at this conference if that's your jam. So, now, without going too far down a rabbit hole, I'm going to give you some history of AI and how we got to the kind of AI that I'm going to talk about. So, we have to go and have a look at the classification of our AI first. So, we have ChatGPT somewhere on here. No, that's on a different thing. That's not a narrow, that's a different type of AI. But we have Grammarly. People have seen Grammarly. That's an expert narrow AI. We've got Alexa, and right up to AlphaFold, which is doing protein folding. So it's superhuman, can do things better than a human. But actually, we are looking right back here at emerging narrow AI, sometimes called good old-fashioned AI. All right, so it's better than an unskilled human. All right, so as I said, it's called good old-fashioned AI, or logic-based AI, or classical AI, or symbolic AI. Now, that would be the name that is most sort of used, I would say, in the circle is a symbolic AI, because we're talking about symbols. Okay, so what does that mean? So here we're going to go back in our history, all the way back to the first AI summer. We're not in that now. We are actually in the third AI summer. The second was in the 1980s. So the very first AI boom was back in sort of 1948 to 1966. So, Yeah, but nothing new happening. So we're going to talk about GPS, not global positioning satellites, okay? General problem solvers. So this was one of the earliest AIs, and that came about in 1957. Now, Alan Newell, J.C. Shaw, and Herbert A. Scheinman did this at the Rand Corporation, and they built this as a... Oh, it's a walkie-talkie. I was like, what? The machines are coming to get us. So they designed this, and this is designed to problem solve, as the name might say. So what is a symbol? These are symbols, bless you. We can think of these as nouns. We have like a trophy, Game Boy, a person. We can name all of these things. So it represents a set of problems as a set of states, operators, and goals. And then it uses I can never say this, heuristic to find a sequence of actions that would give you the way to get to your goal state. Okay, so we can break things down into sub-goals and go through all of those. So if we come along, what does that look? We have a relation. So we've got our sunglasses and how they relate to a man. And if we pass in the man and the sunglasses, and that's true, he's cool. Okay, so we can see that. He's cool, all right, definitely, okay. So it used some kind of means and analysis. So what do we mean by that? We've got GPS calculations, and this is going to look very similar. Now you can see where the logic-based AI came into it, okay? False is a 0, true is not 0, okay? It can be anything other than 0, and is multiplication, and or is addition. So if we come in here, is the kid wearing a cool old hat? So how does that work? So if it's an and, okay, so we need to have the multiplication at the top, because we said it was and the ones and zeros. So here you can see that we've got true for the hat, true for the old, okay, true for the cool and true for the old. So it is a cool and old, and the kid is wearing it, okay? So we get that, all right? Then we come down. If the hat is cool, but it's not old, then this statement's not true. And again, through the others, it's not true because it's a multiplication. So this has to only be the two things. It's an and. So you can start to see how we could program that, right? So now we're going for an or. Is the kid wearing an old or a cool hat? And then here we have the addition this time. Doesn't matter which one, and then the multiplication. So you can see, as logic would predict, that we're going to have more trues than falses here, okay? So now we can see that. We can build on that and go to the next stage, which was expert systems. Kind of similar, but it was the next logical progression. And you may have heard about expert systems. They came about in the 1970s. There was MySyn back there, and that was about medical expertise. And these are basically a lot of knowledge bases. So they would put all of this knowledge about medical diagnoses into a knowledge base, and then it would work on if this, then that, okay? If they had this symptom and this symptom, this is the diagnosis, that kind of thing. So it didn't have any common sense. It had a knowledge acquisition bottleneck, so they called it. You have to get the knowledge into the machine. There was no learning. It had this fixed knowledge, okay? So whatever you put into it, all those states, the diagnoses, had to be put into it. So new stuff that came back, new research had to be loaded into the system. And it totally wasn't adaptable. It required a lot of manual intervention, okay? Now, talking about these, you may think that none of this is intelligent enough to be called AI by modern standards, but it is absolutely AI. You cannot debate that. This is absolutely classified as AI. Okay, so if we come on to why I went back to this and why this influenced our video games? Well, the GPS inspired AI planners and search and algorithms, such as A-star pathfinding. We're going to have a look at some A-star and how that works, and HTN, hierarchical task networks. Yes, I said that word. So this is what NPCs can use to navigate around your game levels, and also how they make decisions, okay? The expert systems led to rule-based AIs based on that if-then logic, and that's sort of behavior trees and GOAP, see, goal-oriented action planning. So we'll go into that too. And they both contributed to heuristic search techniques, okay? So all to how game AI agents, NPCs, make decisions. So let's go into some core techniques. And the very first one is a finite state machine. FSM, okay? We've got the alphabet soup. Does that give anyone else goosebumps?
Can you show the face slowly turning to water?
I love that. Okay, so I am of course talking about Half-Life, all right? Every time I hear that Valve intro music, I'm like, oh, I've got goosebumps. I'm like, oh, I'm gonna get to play Half-Life. Oh, it's not Half-Life, it's some other Valve game. But anyway, Half-Life came out in 1998, would you believe? That's like nearly 30 years ago. That's terrifying. So it wasn't the first game to use AI, but it was really a defining game for how AI worked. The NPCs, known as monsters, whether they were the scientists or the actual monsters, all derived from a monster class, and then that's what they used to control them as an FSM, a finite state machine. Okay, so what is it? This is a way to switch between different states. So it could be, let's go with a monster. They're patrolling, and the state changes. Gordon Freeman is visible. So now they go into an attack state. They're injured. So now they have to go into a fleeing state. Gordon Freeman is dead. They go into a party state. You know, this is how we move through our states as we go on there. So it's a method for synthesizing sequential circuits. Was a paper that came out in 1955, and this was one of the starting points of the FSMs, okay? There's two very similar ones, very similar names as well, Mealy and Moore, different times. So it's very deterministic. That's quite an interesting thing about it. And they vary very subtly, and the subtleties are a bit lost on me. But the output values are determined by both its current state and the current inputs. So that would be the state, I'm injured, and any current inputs that it has. So we can always determine what the next state would be based on that. So the other one by Moore is the Gedanken experiments on sequential machines. What a name, Gedanken. I probably mispronounced that, but it doesn't match. So you can see that that was also in the 50s. And this is current values, output values are determined only by its current state. So there's no looking at inputs. So they're not new. They've been around for a long time. Pac-Man used FSM. So you see, it's been around for a very long time. So they switched between the chase and scatter and frightened states. And that's how that worked. But absolutely every game that has a character that you control uses an FSM, and that is through player movement animation states. Okay, this is the most common FSM you will have. Okay, you're idle, you're standing still, you're either running and you're going back to idle, or you're jumping from running and you're falling back to idle. So we have this loop here. You're only in one state, and it changes based on the player input, okay? So you can see that this might get quite complex quite quickly if you had a lot more states. So that brings us on to a slightly different version of the FSM, which is hierarchical. They like to throw in a lot of complex to say, or difficult to say words in AI, I think. So as it gets more complicated, we want to go into this hierarchical FSM, which gives you hierarchy. So let's have a look at the picture. It's always easier with pictures, isn't it? So here you can see a much more complex FSM. And basically, all it means is that we've got sub-FSMs. So we go from our idle to our duty state. So that means there's no Gordon Freeman lurking around. We're just going through our animations. And that's patrol, cook, research, and sleep. And they can transition between any of those states. There might be another state, which is where they'll wander about, and then they might spot Gordon Freeman then, and then they will go into a combat state. Based on various inputs, they'll switch between getting into cover, rearming, ranged attack, melee attack. That's all based on distance. And now you can start to see how the inputs affect which state. And then it can transition between all of them. Looking kind of complex now, isn't it? Okay, but we'll address that as we go along. We'll choose some different models to use. All right, so I promised you that I'd give you some ideas for your business apps so you can have an excuse to play with some game dev, okay? Chatbots. IBM's Watson for customer service used FSMs, so you can go and do your own one. It did also bring in some ML and NLP, so you can tick those boxes at work also. Robots, they are the best example of FSMs, okay? They go through that on assembly lines, different states based on different states of, say, the production line. And then the retail self-checkout systems. I hate those. Is the customer scanning? Yes, we'll beep. Are they finished? Please present your payment method. Okay, please present. Take your shopping. Oh my God, okay. I hate them. Do you have them here? Okay, good. They're like a blight on the world, aren't they? Okay, so you can see now you can blame those people in the 50s for them. All right, so that is the most basic thing. That's probably what you will start with on your MPCs, a state machine. When you get a little bit more clever, or it's getting more complex, and you're like, my brain is melting, that happens a lot in game dev, we go on to behavior trees. Now, this is also known as a directed acyclic graph, these words. And this is a collection of nodes that are connected. Get those mixed up. So it has a very fixed direction. We flow down through the tree, and it includes various different types of selectors, sequences, and decorators, and these control the execution flow. So let's have a look at this in a picture. So we've got the start at the top, known as the root. And then we come down into a sequence. So we've got a sequence of leaf nodes there. You can have a leaf straight off the root. You can come to a selector, and you've got a leaf, the decorator, and a leaf. So that's kind of how they look. So let's go through and explain what each of those are. So a sequence means and. So if we look at this, we have to satisfy all of those leaf nodes, okay? We have to do all of them. The sequence is the or, so we can do either the leaf or the decorator on the right-hand side there. Okay, so they always evaluate from left to right, and if in a sequence, if one child node fails, it returns a fail. So if any one of those three failed its checks or whatever it's doing, the whole sequence would fail. Conversely, with the selector, it will start on the left. If that one passes, the node passes. If that one fails, it goes on to the next one to the right, and so on until they either has a pass one or they all fail. So that's how they work. Now, I lied. You can have them randomly select children. You don't have to have them go from left to right. there's a lot of these lies. This is the rule. No, it's not. Ha, fooled you. So this happens a lot in AI, in video games. It's hurt my brain a lot over the past 18 months. So you can randomly select it. And then we have the different types of decorators. So these control the flow to the nodes beneath them. So we can have an inverter, basically, if it was true, it's now false, and vice versa. A succeeder, so we don't care if it passes or fails, it's always going to pass. Yay. A repeater, basically a while loop, it will keep doing that action until it fails. Or it will keep doing it until something changes, and then we have a repeat until fail. So it will keep doing it till it fails. So we can see how we can start to build these quite complex behaviors. Now, if we look at a leaf, it has no children. That is the definition of a leaf in a behavior tree. Okay, I need to say that the leaves have different rules depending on which AI structure you are using. It contains the action, and it performs a method. A perform method will be ticked. Now, a tick is something that we use commonly in game development, and that means we'll do it every cycle. Now, that cycle could be every frame. It could be on the physics update, which is usually every 4 frames because it's expensive. We don't do that very often. It could be every second. It could be every 10 minutes, whatever the developer defines. But we tick this regularly, okay? And so you can see it's basically an if statement. If has reached the destination, yay, success, we return the success, okay? If they've run out of time, boo, they failed. And if it's neither of those and we've still got time left, we'll subtract a time. Time.delta time is a way of normalizing time, because if you've ever played video games, you know that your frame rate goes up and down. So if you were doing this every frame, so we're going to do whatever this frame is, you get a mismatch on time. So we do it on this thing called delta time, which is the time the frame took, okay? So if you see delta time in there, that's what it means. It's a way of normalizing the time across all your frames. It will be running. So it's either passed, failed, or it's still doing its thing. And that's how we determine the state of that leaf. Okay. Now, how do we store all of these inputs that are coming in? Now, it's something called a blackboard. So all of these states that are going into our AI systems, whatever they are, need to be stored somewhere, and it's in memory. Now, when you save your game, it's writing all of these values off your blackboard into your game save, sort of into some format, binaries or JSON or something like that. But many systems will use a blackboard, and it can be as simple as collections, a whole class full of dictionaries and collections or values, bools, anything like that. It's nothing fancy. So we use those a lot, okay? All of the systems I'm going to talk about today will work off a blackboard. So if we look at the difference between behavior trees and an FSM, finite state machine, we can see that the behavior tree is very modular, very hierarchical. You can follow the logical paths down. It has the use cases with complex AIs, so it helps with the NPC decision making rather than just, say, changing state for animation and that kind of thing. They can both become really complex. Things with behavior trees as well, once they get down too many layers, it can really start to go nuts, okay? So usually once you get past 100 layers, so that's 100 layers in your tree, you need to be switching something else. Imagine developing something that's 100 layers deep. There are quite a lot of games that are like that. Is it Balatro? That card game recently. Yeah, that is, someone decompiled the source code for that, and it was just if, the whole way down, apparently. So they can get really, really difficult to maintain and manage. So with the FSM, it's simple, it's predictable, easy to implement, but you can't scale it. So it's really good for those animation transitions, or if you have basic enemies doing some, basic patrols. They're going to stand there, walk there, whistle here. You can have them go through those very basic things. But if you want them to be a little bit more responsive, you're going to need to switch to a behavior tree. Okay, so in your business app with behavior trees, customer recommendation engines would be a one, and again, for process automation, robots. We owe a lot to the robotics industry in the game industry. So much comes from robotics. So those are sort of the easy, basic ones. And you might have used very similar techniques in your business applications as well. It's nothing sort of very specific to game development. Okay, so now we're going to go on to advanced decision-making techniques. Now, this is where brains start to melt. I found my brain had to learn how to be more muscular and effective when I started going into these. But before we go strictly into that, we're going to segue to NavMesh, because it's an important thing to know, because we use some of the algorithms in that for our later AIs. So NavMesh, let's think about Grand Theft Auto 5. If you've played that, who's played that? Okay. So when the people are walking around on the street, they don't walk down the middle of the road, do they? They walk on the pavements. They use crossings. You're thinking, wow, that's clever. Look at them using the crossings. It's great, okay? I was like, oh my God, this is amazing. And that's because they have NavMesh under there. And we have different weights on different nav meshes. That's how we can make our NPCs walk on pavements and cars drive on roads, and not everywhere unless, something happens. They'll prefer to do it. Doesn't mean they won't do it. Okay, so if we come on here. Okay, so this is a demo I did actually for bug fixing. And here you can see this is one big nav mesh. And the pink is the priority. An agent will prefer to go on the pink line. Can you see the little guy moving around up there? He's quite tall. I couldn't zoom in on this. It was an old video I had. And what he's doing is moving around these structures. So what happens is they choose a random point. It has to fall on the blue nav mesh, and then we'll walk to it. They will prefer, especially here, can you see? Oh, go back. It's going to here. Let me go. Play. No. Broken it now. There we go. So watch when they come down to the bottom. Well, you can see it right there. They are walking along the pink and then navigating up to the top. So they won't just cut straight across. They'll try and stay on that pink line until the last possible minute. So that's how you get your NPCs to walk on it. So how did this come about? How did we get to have this nav mesh and NPCs moving around on it? Well, we have these things called Voronoi diagrams. If I've said that wrong, someone can tell me how to say it. And that was after a Russian mathematician. So he studied the general n-dimensional case in 1908. And what happens here is we have, you see all those dots? It may look like cells. Ever looked at cheek cells or leaves under a microscope? Doesn't it look like this? It looks very organic. And this is kind of how this works. We have that nucleus. And what the program does is start to expand out into the space until it hits another one. Okay? So every one of those black dots is equidistant from the other one across its border. Can you see that? Because they've grown at the same rate until they've hit their boundaries. So this is a way of dividing up spaces. So it's very organic. There are a couple of different ways that you can have, but it is based on Euclidean distances. And so this was part of pathfinding for robotics. So it's a very useful way of dividing up your spaces. So we then go on to meadow mapping, which was first described by Ronald C. Arkin in '86. And again, this was for robotics. The area here is divided up into something called a convex polygon. That is basically a shape that if you draw a line across any of it, it's always contained within the shape. That building wouldn't be a convex, because if I drew from the top to the bottom left, I would cross outside of the shape, okay? But all the other ones that have been defined in there, if you draw a line across any of it, you'll be inside the shape. So what we have here are just all these shapes, and that was another way of dividing up the area, okay? And then we come into Quake's area awareness system in 1996. And that was developed at id Software, likely by John Cormack and John Cash. And again, we have these convex polygons, usually by rooms in this case. And they call doorways portals. So if we have the agent on the far left, you can see that they go to the middle of the portal, and then they will cross from portal to portal. And that's why it's really important that these polygons are convex, or else they can't do this. So you'll notice that these agents are always going to travel in straight lines, and it's going to be very angular and not very natural. So building on these different techniques, we get to modern nav mesh systems. So they didn't really use much of the meadow mapping. It was more the Voronoi and the area awareness system. But we have now a lot more interconnected polygons for NPCs to traverse across, and we get this more natural movement, okay? So it gives them a lot more options, and it's a lot smoother. So how does that look? Okay, so this is a screenshot from my game, The Third Tourist, and this is a cross-section of one of the buildings, and the blue here is nav mesh. So we can see the grid, the big squares, they're easy, you can understand those, and we're going to start zooming in on the interior of this house. This is an upper layer, so you can see how we've gone up a floor, and we've still got all of that blue. Now, if I take away the geometry, this is what the nav mesh looks like, okay? So NPCs will follow this nav mesh. They don't need any geometry at all. They're not walking on the building blocks that you put in here. They are walking on this mesh. You can do this anywhere. They will walk on this and this alone. They don't care that there's no geometry at all. And you can see the stairs are just a slope. We've got it all interconnected. And then if we start zooming in, this is what it looks like at the stairs. And it's based on the size of the collider capsule on your NPC and the gaps that they can move across and the height that they can step or jump. Okay, so we've got these sort of limits. You can see that's why it's narrow at the top of the stairs, because there's some boundaries there. There's some pillars that would be in the way, so they can only go through on that narrow bit, but they can still go through. Their collider will fit through there. And if we zoom in again on the doorway, can you see all the polygons, all those lines? Yeah? That's how we've started to divide up the nav mesh to enable the pathfinding. Okay? So how does that work? This uses an A-star algorithm. And if we come on to have a look at this, I shall attempt to explain how nav mesh pathfinding works. This is not a periodic table, I promise you. We're not going to go into chemistry. Our goal is to go from the start to the end. The black is a non-passable path, okay? So we have to route round it. So what do we have? If we look at a node, which is in the top left, we have the F cost. That is the total cost. In that case, it's 44, and the observant of you might notice that that is the sum of the G cost and the H cost, okay? And F is the full cost. So the G cost in the top left is the distance from the starting node, and the H cost is the heuristic, I got it, cost, and that is 34 in this case. So the total is 10 behind us, 34 in front of us. The total distance is 44. All right, so let's do a start. When we put all of these distances on, for ease, we're saying 10 up, 14 across, because it's 1 crossing and 1.4 across. So it's easier if we just multiply that by 10 and have 10 and 14. So if I go straight up, it's 10 from the start and 24 from the beginning. So that is straight up and across. So we go up one, up another into the black thing, and diagonally across to the end. We can't do that because there's the black thing in the way, right? So that's why it's red. It's a closed node. It's been evaluated. So now we're going to go to the next lowest F cost. So that is the top left corner. That's 14 from the start and then 20 from the end. But again, we can't do that because there is an obstacle in the way. So we keep working our way around. And as we do these, the green nodes, the unevaluated nodes that are open, updates. So now let's go from the start, and we're going to go left to the 40. And what you can see there is now the bottom left and the bottom middle, their values have updated because now they are what the distances are if you travel via the one on the left, okay? So as we start moving around, the paths start updating. So this would be go left, down, and right and across. And quite quickly, we can see, well, if we do that and we go across left and down one, we're at 60, but we've got a 42 in the top right. So we're going to stop evaluating that. It's not going to be better than the 42 at the top right. So we now go and evaluate that. So it's 14 across, and it's 28 to the end. And that's how we continue. We keep evaluating, and the red ones are evaluated and determined, no, they're no good. So the one that's the red 82, we would have evaluated that one and the blue 82 and determined that the blue 82 has the lower distance to the end and is going to be the better option for us. And that's how we can find the blue path all the way around to the end. You can see we've got 82, 82, 82. That is the cost of that movement, okay? So that's how that works out. And that's going to help you as we go into these more complex, high-level systems. So the first one I mentioned back at the beginning, goal-oriented action planning. I spent all of last year and a bit of the year before trying to get my head around goal-oriented action planning. Okay. The theory, once you get it, yeah, that makes sense. Try implementing it, okay? It's, alrighty. So, affectionately known as GOAP. This first came out in Fear, First Encounter Assault Recon. So that, I'm really sorry for the fuzzy images. It's what I pilfered off Google. So we have Fear, and what is going on behind that? All right, so I just missed one. Jeff Orkin is well famous for developing GOAP, okay? He was, I think, like a level designer or something. He'd never done AI, and he moved in, and they said, right, you need to work out how all of our enemies are going to behave. Off you go. So he locked himself in a room for 3 months, and he went through STRIPS, Stanford Research Institute Problem Solver, and came up with goal-oriented action planning. It was a planner, basically. And it took him a year to write this. He only focused on this. And they kept saying, oh, is it ready? Yeah, it'll be ready, it'll be ready. He still had no clue. Okay, so he basically says, there's loads of interviews on Jeff Orkin's experience of how he developed this, okay? So it's really hard. So we have an initial state, like we've spoken about. We have a goal, and then we have a set of actions, and they have preconditions and postconditions, okay? We'll cover those a bit more as we go. So what we need to do is we have a goal to satisfy or reduce hunger. Our preconditions are things that we need to check. Do we have a cooking facility? Is there money? How close to death are we? Are we about to die from starvation? And then we will look at the possible actions. Eat raw vegetables, okay? They might stave off starvation, but they maybe won't give you a health boost. You could cook dinner for a really hearty meal, or you could buy a takeaway. Oh, I forgot to correct that. Excuse the lacking you. Buy takeaway. I knew there was something I needed to fix. But anyway, so based on those, if we don't have money, we can't buy a takeaway. If we don't have cooking facilities, we can't cook dinner. If we are about to die and we have a carrot on us, we should eat the carrot, okay? That's what starts to come out of it. And fear has been decompiled, not decomposed, and you can see that it has a few very simple goals. This is all it has: guard, kill enemy, dodge, cover, and ambush. And then all the actions that can satisfy that. Let's have a little watch of gear. This is the video game violence, okay? So if you don't want it, close your eyes. Let's go. All right, so I'm going to commentate on this because this was a really good YouTube commentary on the AI. I've got links all on a thing for you. All right, so here we are. We're hiding behind a box and we're shooting enemies. They're flanking us. So there's the first thing. They are coming from both sides. So we're trying to flush them out. That enemy has low health points, so is now trying to flee. But they are still coming and flanking us again. So you can see it's really intense gameplay. So they keep doing this, and you push them back. All right, so they're trying to get to you in cover. Now, this is a new bit. They can see if you've got your flashlight on. And then they push over things, okay? So they're watching here. Let's go see what happens. The music makes it tense, doesn't it? You're like, are they going to come there? So we've got them hiding in cover. There's the bit I want there. Ah, yes, this is the interesting bit. So he's killed someone that way. Watch this. Coming up. You have to be quick. It's going to come. I'm building the intensity. See that? Did you see it? He pushed over a filing cabinet to create cover. I mean, how clever is that? It's what you would do if you were a super strong soldier, wouldn't it? You'd go and push over this massive metal filing cabinet and hide behind it. So you can see there, they're flanking. They appear really, really intelligent. Have you got a question? Go.
Can you comment maybe on the fact, like, in current video games nowadays, we don't even see this smart stuff anymore, even if this was done so long ago. Why don't people do this?
Because it's hard, and they're trying to churn out games really quickly, okay? And they're just like, oh, yay, let's just shoot everything. Yay, let's go nuts. There are a lot of games that use this type of techniques. Off the top of my head, Far Cry would be ones that they're really intelligent. I love in Far Cry 3 and 4, the attacking the outposts. You're really going for those, and it's really clever. Lobbing in meat to attract the wild animals to go and kill. All of that is really intelligent. They're doing all of this type of thing, but we'll carry on to those. So at the moment, you can see how long video games are taking. That's because the really good ones, this stuff is really hard to program this and to make good games. But if we talk about what this type of game and the games that do this share, they're emergent. So you don't know what's going to happen. It's not deterministic. It's not predictable. There's so many moving things that get you onto there. They're unpredictable. They are real. They feel like they're actual living people plotting and planning your demise, okay? They can perform multi-step things. Like that guy, he's like, okay, I'm injured. There is no cover. I need to knock this filing cabinet over while my squad mate goes and flanks, and then I can shoot them. So we have this whole sort of thing going away. They're aware of their environment. So it does sound like a behavior tree going down, but it's not, okay? It is very different. So we have Far Cry 2 is known to have used GOAT. Stalker, Shadow of Mordor, The Sims, And Prey, one of my all-time favorite games. If you have not played Prey, go and do yourself a favor and play Prey. All right, so how does this work? We're going to start by looking at some dominoes. I'm going to move on because we've got a lot to cover. We have a condition, we have a goal. We start at the goal when we do GOPE. All of these satisfy our goal, 7. That's our goal, okay? Dominoes is the way to start. We then work backwards, and you can see, well, I've got a 2 on the side. That doesn't match my starting condition. What does? We have another domino, that's 2. It has a 5. Oh, there's another domino that has 5, and the 3, which is our starting condition. So you can start to see how we work back. Each one of these would be considered an action. We've got our goal, and now we've got our sets of actions, okay? So that's an important step to get in your head of what we're going to do in a moment, okay? So we need to break this into 2 things, goal selection and action planning. This is our goal selection. Alrighty, so goals are sorted by priority, which has the highest priority, and that is based on a whole load of factors off the blackboard. That can be your health, hunger, emotional state, whatever the developer and the game designer has determined. And they are sorted by priority. So we take the top goal, and we're like, is the priority of this goal more or less than the current goal? If it's less, we keep the current goal. If it's more, we're going to go into the next stage and see if it can run. Things that mean can it run at the start are like, this only runs at nighttime. It's daytime, so you can immediately dismiss it. So that goes on to our action planning. All right, so we go through and get all the actions that could satisfy our chosen goal, okay? And then we start to work through those. Okay, so these are all the ones that had the 7. We are not talking about the others. And we start going through what's their condition, what is their effect. The condition is what it needs to run. The effect is what happens and how it changes the world once it has run. And so we go through all of these stages, and then if it can run, we add it to our pile. If it can't, we dispose of it. And then, we're still not there, we're on to the other bit. Okay, so now we've got nodes again. And it's only the chosen that are leaves now. Okay, remember I said they had different meanings. So that one that's there, a node, that's at the end of a path, that's not a leaf, that's still a node. In this case, only leaves are successful, okay? So we go through all of this plan. So everything has a parent, it has, unless it's the starting node, it has a cost, it has an effect, and an action. So that all fits in with that action planning. You'll see in a minute, the A-star pathfinding. So in this case, we found 2 possible actions that would satisfy our goal. That's leaf 1 and leaf 2. So we've gone down through all of this, and we've got these things that will help us, okay? So then that comes on to the final stage. So we've got node 1 and node 2. That's leaf 1 and leaf 2, okay? So we're looking at those 2 nodes, and we want to now return the cheapest of those. So remember that carrot and like the takeaway. We're now going to look at which one's the cheapest to run. Now that can be based on distance, so that's a heuristic thing. So how far am I away from that object, okay? That's how they can choose between doing one task over another, because yes, at this time I could chop wood, or I could dig up grubs, I don't know, okay? So which one? Oh, okay, well, I can do either of those. Digging up grubs is right here, so I'm going to do that. It's the cheapest because it's the closest. So when I say cheapness, I can talk about what's the closest, any kind of value that we put cost on. So once we've got the cheapest, we then traverse all the way back up. So if it was leaf node 1, we'd be going up the node. So we could see that there's 2 nodes after that. These are all the actions that now make up my action plan. Okay, so we've gone back up, and that's why it's known as a reverse algorithm, because it's a backward planning graph. Okay, we start at the end and we go back up. Okay, so if we come here and look at this A-star pathfinding again, you can see how that had a big impact on how this works. So GOAP uses, under the hood, A* pathfinding. Okay, so we're finding that cheapest action, or the ones that satisfy our goal, and then we're finding the cheapest. Okay, it's expensive, I will say that. So here it is with that A*. You can come down. We've got the current node. Can it run? No, we forget it. If it can, would the goal be satisfied? Yes. Okay, that's a positive leaf. If it can't, it's not a leaf, it's a node. Does it have children? Okay, we're going to start this whole thing again. That current node becomes the parent, and it's recursion. So you go really deep, and this is why it's expensive. We're going down every possible pathway that we can until we get all the positive leaf nodes, okay? And that's why it uses A*. Okay, if you are nuts enough that you want to use this in your system, smart scheduling is the thing that comes to me. If you're building an HR type program and you want to plan everybody's holidays and things like that, this would be a good way. It would take in a whole load of different factors, like do they have holiday available, what hours they work, is someone else on holiday then, and you could make it work out. Logistics, delivery, customer support, there's loads of different ways that you could make your brain hurt and implement this, okay? Its cons, it's unpredictable, it's not deterministic, okay? It is difficult to design the player interactions because we don't know what these crazy NPCs are gonna do. And it is very expensive to run, so you need to think about that. And that's exactly what High Moon Studios did when they came to design Fall of Cybertron. They used, in the previous game, War of Cybertron, GOAP, okay? But they ended up having their designers go in and design, come out of the GOAP system and make some sort of behavior tree to control endgame interactions because the GOAP was too unpredictable for their game design and ideas. So that's where hierarchical task networks come in. And this is actually what I have shifted to because GOAP was being too unpredictable for me. And in January, we switched to HTN. And it was so much easier. Okay, so it enables structured problem decomposition. It can be very specific to domains. It has all that goal-oriented flexibility. We have goals. It's more efficient because you can control the way it goes and you can design it so it fits your narrative. So GOAP is really good for crazy simulations like RimWorld, whereas HTN, if you are telling a story but you want more emergent gameplay, it's going to help you, okay? So let's go on. How does it work? Well, we're going to use a different type of algorithm here. It can evaluate all possibilities and return partial plans. So that's really a nice thing. It doesn't have to go all the way. It's like, yeah, we can do this now on the way to that route, so we'll start that. Here's a partial plan. And it can keep reevaluating that state as it goes, so it can be less expensive. And it looks like this. Yay, isn't this nice and simple? Okay. All right, so orange are the conditions that are needed to go down that node tree, okay? So if at the top there, let me see, that's too small. So we have, do they have an enemy? Is the enemy in range? Okay, those are the factors that we're going to look at. So we're going to attack. If the enemy is in range, it's melee range, and do we have a tree trunk? Are we still traveling to them, actually? As the navigating, we're there. We're in front of our enemy, okay? We don't have a weapon, though, but they're in melee range. So we're going to uproot this tree, and then we're going to hit them, okay? But our tree only lasts 3 hits. So we start taking on the do trunk slam. Can you see that? We're taking off some health. And then when that finishes, we have to uproot another tree. So we've got this like nice dynamic behavior. And then if the player moves out of range, well, this is no longer satisfied, so now we're going to go on to other ones, ranged attack. And we can keep going through that. Now, this is from a really great white paper. I've put a link in all the lists that we go. And this is like the troll, bridge troll idea. Okay, there's some great demos on it and everything that explain it. But what is going on under the hood is that we have our depth first search algorithm. So we start at the root, we go, can we do it? We keep going down, and we go all the way through. So we are building it downwards. We're not getting the end goal and going back up. Okay, so as we step through that, can it run? Are our preconditions met? Yes. This is a good path. So you could stop there. You can just get the first path. It moves right to left like a behavior tree. And you can ignore everything else, which you can't do with GOAP. Okay? So games that use this are Killzone 2, Killzone 3, Horizon Zero Dawn, Dying Light, and rumored Dark Souls. Okay? So you can see a lot more modern games are using this because it's much more easy to control than GOAP. And in your business app, project management, construction planning. All right, so if we look at GOAP versus HTN, one is backward planning, one is forward, one is less expensive. And it really depends on what you need your NPCs or your business app to do. All right, so we have minutes left. So we're going to whiz through these next things and look at complementary AI systems. I'm here till sort of early afternoon, so if you want more information, you can come and grab me. So complementary systems are ones that work with all these other AIs. The first one is director AI, and it does whatever you think it sounds like. It's going to direct the gameplay. It sits above everything. Alien Isolation used this beautifully to control tension and gameplays. Far Cry uses this to despawn NPCs and animals that are outside a 200-meter radius, so you're not loading up the system. So it's controlling where the NPCs are and what's showing. Left 4 Dead did, clicked on too many. Left 4 Dead did this by controlling the tempo. If you want to watch this, go and watch AI in Games, Tommy Thompson's review of Left 4 Dead and Director AI. Okay, links for that in my link document. And he will tell you how it controls the pace and the tension in the game via a Director AI. And then we have utility AI, and this one is flexible decision making. So things like the Sims will use this. When you can do multiple things, what would be the most natural human-like thing for that NPC to do when we have multiple choices? So it goes on and controls that. And there are several games that use that. Again, Alien Isolation uses this to control the speed of the aliens' animations to, again, build tension. And then we have hybrid systems, which use a whole load of these. You can have GOAP inside HTN if you really want to kill yourself and do all of that. So as you probably already got, that my personal experience has been brain melting. I've got brain melt down there, okay? But I have been able to write much more performant code. My development skills have gone from, I'm a middle-of-the-range senior developer to, oh my God, I could melt you all with my brain power kind of feeling, okay? I come at problems from a really different perspective now. I have much more sympathy for the machines. I think about things I never thought I'd have to. Garbage collection is the bane of my life. I am writing unmanaged C# because it's more memory efficient, okay? So there's all these things I never thought I'd have to do when I was an enterprise developer, and now I have it. And this is why you should give it a go, okay? You're going to expand your problem solving. You'll change how you think about your systems. You'll get so much better at debugging because when you look at this and NPCs are like twitching and doing weird stuff, you're like, I don't know where to put a breakpoint. And then Unity explodes and everything goes wrong and things are disappearing and flashing happening and you're just like, but you get really good at looking at diagnostics and analyzers and debugging and everything. And you know what, most of all, it's fun. Yay, I do 70-hour work weeks, but I love it. So I would say give it a go. There's lots of things that you can do, loads of tutorials like on the Unity. Don't worry about all the kerfuffle that happened with Unity a while back ago. It's still, as C# developers, it's going to be the most fun for you to do, okay? Now, this is what you need to take a photo of, or the bit.ly /forgotten-AI-video-games, and everything in there, including the slides, I think, are all in there. Loads of links to documents, white papers, YouTube videos, everything you could possibly want to dig deeper into what we don't have time to do today, okay? Because I've gone over and I never go over. And then I have a favor to ask. The Third Tourist, please wishlist it. Please wishlist it. It's just me and my husband living off our savings, writing this video game, and we'd really like it to be successful. If you want to see devlogs and how I do it, all the links are in the document as well. November North Games, I do semi-regular devlogs on how that. We talk about the AI systems, the mini games I'm building, all sorts of things, and everywhere with that. And I just want to say thank you for hanging out with me. It's been great. And right, whew, wowzers, that was so much to get through. Thank you.